Hi guys, I'm Mr. Joseph, your chemistry teacher. So in our today's lecture, we'll be looking at electronic configuration, we'll be looking at electrons, energy levels, atomic orbitals. So at the end of today's lecture, I think students will understand the terms shells, subshells, orbitals, principal quantum number. We'll talk about the ground state limited to electronic configuration. Then we're going to describe the number of orbitals making up the S, P, and D subshells, and number of electrons that can fill S, P, and D subshell. Then we're going to describe the order of increasing energy of the subshells within the first three shells and the 4S and the 4P subshell. Then we're going to describe the electronic configurations to include number of electrons in each shell, subshell, and orbital. So please, I want us to listen attentively and get the best out of this lecture. We're also going to talk about the shape of orbitals, the shape of the S and the P orbitals, and so much more. So please, I want us to pay attention and listen attentively and get the best. So we are looking at electronic configurations, having considered atomic structure. Now we want to look at, the Bohr's model, Bohr's theory. Now the Bohr's theory sees the atomic structure as a small nucleus of protons and neutrons surrounded by circulating electrons. If you look at the atomic structure, electrons are arranged on the shells, starting from the innermost shell to the outermost shell, which is the K shell, which is the first shell, the L shell, which is second shell, M shell, third shell, N shell, and fourth shell. Just, it continues like that. So each shell or energy level could hold a maximum number of electrons. Yes, each of the shell could hold a maximum number of electrons. Like the first shell can hold a maximum number of 2 electrons. To determine the number of electrons that a shell can hold, we use the formula 2n raised to power 2, where n is equal to the number of shells. So if n is equal to 1, which is the first shell, so it will be 2 bracket 1 raised to power 2, which is equal to 2. So the first shell can hold the maximum number of 2 electrons. The second shell, if n is equal to 2, so we'll have 2 bracket 2 raised to power 2, which is equal to 2 times 4, which is equal to 8. So the second shell can hold the maximum number of 8 electrons. The third shell can hold the maximum number of 18 electrons. The fourth shell, which is 2 bracket 4 raised to power 2, which is 2 times 16, which is equal to 32. So you can hold the maximum number of 32. So with this formula, we can determine the number of electrons that each of the shell can that each of the shell can hold at a particular time. So the energy of levels become greater as they got further from the nucleus, and electrons feed energy levels in order. So you start from the innermost shell, which is the shell with the lowest energy level, to the shell with the highest energy level. As you move from the inner shell to the outer shell, the energy level increases. So with this, we can draw the electronic configuration of a particular element. Once you have the atomic number, so you can draw the electronic configuration. Like if we are to take sodium, for example, sodium is Sodium is 11. So the first shell will take 2, which is the innermost shell, which is the K shell, the shell with the lowest energy level. The second shell will take 1, 2, 3, 4, 5, 6, 7, 8, which is the second shell can take 8 electrons, and the third shell can take 1 electron. So that means sodium as an element belongs to group 1 because it has 1 electron in the outermost shell, and it belongs to period 3. 1, 2, 3. The period is the number of shell, while the group is the number of electrons in the outermost shell, which is the valence electron, which is the number of electrons in the outermost shell. So each shell or energy level would hold a maximum number of electrons, and with the formula you can get the maximum number of electrons that each shell would hold, and you can simply draw the electronic configuration configuration. So if we are to write the electronic configuration for sodium to be what? 2 what? 8 what? 8 1. So this is the outermost electron. This is the first shell, the shell with the lowest energy level. Second shell, as it goes from the innermost shell to the outermost shell, the energy level increases. So now, having considered the electronic configuration whereby you draw the shells and arrange the electrons in the shells, starting from the innermost shell to the outermost shell, we want to look at the electronic configuration using the SPDF orbital notation. The S, P, D, and F, they just represent subshells in the shell. So let's look at the subshell name. When we talk about S, the S there stands for what? Sharp, and can hold the maximum number of what? 2 electrons. You just like, each of the shell can hold a maximum number of electrons. So the S subshell, the name source is sharp. It can hold a maximum number of 2 electrons. We have the P subshell, which is the principal, can hold a maximum number of 6 electrons. We have the D subshell, which is diffuse, can hold the maximum number of 10 electrons. And we'll have the F subshell, which is fundamental, and it can hold a maximum number of 14 electrons. So with this, we can write the electronic configuration of an element using the SPDF orbital notation instead of drawing shells, drawing cycles whereby we represent we arrange the electrons. We can use SPDF orbital notation. I know some of you did that in your secondary school where you write the electronic configuration, then you draw the shells. But now we want to look at electronic configuration using the SPDF orbital notation, using the sharp, the principal, the diffuse, and the fundamental. And each of them have its own maximum number of electrons it can hold. So now we want to look at the shell and subshells in detail. Now the subshells, when we talk about the subshell, we have the S subshell, we have the P subshell, the D subshell, and the F subshell. The S represents the sharp, the P represents the principal, the D is diffuse, and F fundamental. Now the number of subshells in the shell is equal to the shell number. I repeat, the number of subshells in the shell is equal to the shell number. Now in the first shell, we have the first shell will have just one S. So the subshell will have one subshell on the first shell, which is S subshell. And S subshell can hold the maximum number of 2 electrons. So that means the first shell can only have a maximum number of 2 electrons, because the S subshell can hold the maximum number of 2. Then on the second shell, we have the 2S and the 2P. That means we have the S and the P subshell. So the maximum number of electrons that the second shell can hold is 2 plus 6, which is equal to 8. So the second shell can hold a maximum number of 8 electrons. Then the third shell will have the 3S, 3P, and the 3D. That means we have S subshell, the P subshell, and the D subshell. So the third shell can hold the maximum number of 2 electrons from S plus 6 electrons from P plus 10, which is equal to 18. So the third shell can hold the maximum number of 18 electrons. Then on the first shell, we have the 4S, the 4P, the 4D, and the 4F. That means on the first shell, we have the S subshell, P subshell, D subshell, and F subshell, which is 2 plus 6 plus 10 plus 14, which is equal to 32. So the fourth shell can hold the maximum number of 32 electrons. So the number of shells in a subshell is equal to to the shell number. The first shell have one subshell. The second shell have 2 subshells, which are S and P. The third shell, 3 subshells, which are S, P, D. The fourth shell, 4 subshells, which are S, P, D, and D and F. So before us are typical examination questions. This is an exam style question. So we'll look at the 2 questions. The first one is name the 3 types of orbital present in the third principal quantum shell. So when we talk about principal quantum shell, it's just the number of shells. The principal quantum number is the same thing as the number of shell. So, and the next question is state the maximum number of electrons that can be found in each subshell of the third quantum shell. So if we go to the first one, we look at the three types of orbitals present in the third principal quantum shell, the third principal quantum number, which is 3s, 3s, 3p, and what 3d. That means we have the s subshell, which is the s orbital, the p subshell, and the d. So these are the three types of orbital present in the third principal quantum shell, which is 3s, 3p, 3d, which are s, p, and d. Then b, you are asked to state the maximum number of electrons that can be found in each subshell of the third quantum shell. So the subshells of the third quantum shell are s subshell, containing a maximum number of 2 electrons. The p subshell, maximum number of 6 electrons, and the d subshell, maximum number of 10 electrons. So these are the maximum number of electrons that can be found in each subshell of the third quantum shell, which are s, p, and d. So we are looking at orbitals. An orbital is a region in space where one is likely to find an electron. Because according to Heisenberg, you cannot say exactly where an electron is. You're only able to say where it might be found. So we can also define this as a three-dimensional statistical map or shape showing where one is most likely to find an electron. Just a region in space where an electron is most likely to be found. Like if you look at the different orbitals, we have the S orbital, which is spherical in shape. We have the P, which is dumbbell. We have the D, which is baryons, and the F is baryons. But we'll be looking at the S and the P, the shape of the S and the P orbital, which is the S is spherical in shape, the P is P is dumbbell. So we're going to concentrate more on the S and the P orbital. So we define orbital as a three-dimensional statistical shape or map where one is most likely to find an electron. So these are the shape of the S and P orbitals. So this is the S orbital, which is 1s. This is 2s. This is 3s, which is spherical in shape. A three-dimensional statistical map or shape XYZ, where one is most likely to find an electron. So as you look at this 1s, 2s, the energy level is increasing. Then look at the p orbital. The p orbital is dumbbell, which is 2px, 2py, and 2pz. Three-dimensional statistical map where one is likely to find an electron. So this is the px, this is the py, and this is the pz. Three-dimensional statistical map where one is most likely to find an electron. So the shape of the s orbital and the p orbital, this is spherical shape. So if you're asked to draw the shape of an s orbital, it is spherical in shape. If you're asked to draw the shape of a p orbital, it is dumbbell in shape. We'll have three orbitals in p subshell. So it is dumbbell, while this one is spherical. So please, I want us to take note: the s is spherical and the p is dumbbell. So having considered shells, subshells, and orbitals, we can represent an orbital using a box diagram. Now, an orbital can take a maximum number of 2 electrons. That is one orbital. It can take a maximum number of 2 electrons, and these electrons can spin in opposite direction. They must spin in opposite direction. So an orbital can take only a maximum number of 2 electrons. So we want to consider the S subshell, the P subshell, the D subshell, and the F subshell, the maximum number of orbitals we can have in an S subshell, we can have in a P subshell, we can have in a D subshell, we can have in an F subshell. Now, from what we just discussed, we say we have the S subshell, that can take a maximum number of 2 electrons, the S subshell. So in an S subshell, it can take a maximum number of 2 electrons. And since an orbital can take only 2 electrons that can spin in opposite direction, so in an S subshell, there is one orbital in an S subshell, just one orbital in the S subshell. Then we'll come to P subshell. A P subshell can take a maximum number of 6 electrons. A P subshell can take a maximum number of 6 electrons. So in a p subshell, there are what? 3 orbitals in a p subshell, which we call what? The px, px, py, and what? pz. So in a p subshell, there are what? There are 3 orbitals. Then we'll come to the d subshell. The d subshell can take a maximum number of 10 electrons. So in a d subshell, there are 5 what? Orbitals in the d subshell, since an orbital can take a maximum number of 2 electrons which spin in opposite what? Direction. So we'll have 1, 2, 3, 4, then 5. So I have to erase this so that I'll have enough space to write. Then for F subshell can take a maximum number of 14 electrons. 14 electrons. So in an F subshell, there are what? 7 orbitals in an F subshell, since an orbital can take a maximum number of 2 electrons that spin in opposite direction. So we'll have 1, we'll have 2, 3, 4, 5, 6, and what? 7. So we have 7 what? Orbitals in an F subshell. We have 5 orbitals in a what? D subshell. And each of the orbitals can take a maximum number of what? 2 electrons which spin what? In opposite what? Direction. We are going to consider it. We are going to look at it as we what? As we continue with what? With the lecture, where we'll be discussing what? Filling or what? Filling of orbital, electron what? Electron filling. So we are looking at electron filling, the process and the principles involved in filling what? In filling electrons. So we say the most stable electronic configuration of an atom is the one that has the lowest amount of what? The lowest amount of energy. That is the shell with the lowest what? Amount of what? Energy has the most stable electronic what? Configuration. So the order in which the subshells are filled depends on their relative what? Energy. You start filling starting from the lowest energy level to the highest what? Energy level. Just as I discussed in my previous slide, that you start filling from what? The first shell, which is the shell with the what? Lowest energy, to the second shell, the third shell, the fourth shell. So the subshell with the lowest energy, that is the 1s subshell. The S subshell is therefore filled first, followed by what? Those that are what? Successively what? Higher in what? In energy. So you start filling from the 1s, then you proceed 2s, you know. So that is it. So the ordering of subshell energies in an atom is given by the Aufbau principle. The Aufbau principle says that what? Electrons enter the lowest available what? Energy level. So you start filling from the lowest energy level to the what? Highest what? Energy level. That is the principle. The Aufbau principle simply means building principle. You build from the bottom to the top. You build from the lowest energy level to the highest what? Energy level. So that is how what? Electrons are what? Filled. So use what? The Aufbau principle, that the electrons enter the lowest available what? Energy level. So still on the Aufbau principle, which is also known as the building what? The building principle, which gives an explanation of how electrons what? Are arranged. You know, starting from what? The innermost shell to the outermost shell, starting from the shell with the lowest energy level to the what? Highest energy level. So the shells, they fill up in the order from following the diagonal arrow in the diagram below. So if you look at the diagram, you have to fill the 1s. After 1s, you go to 2s. After 2s, 2p. After 2p, 3s. After the 3s, the 3p. Then you go to 4s. After 4s, you go to 3d, 4p, and 5s. After 5s, you go to 4d, 5p, and 6s. After 6s, you go to 4f, 5d, 6p, and 7s. After that, you go to 4f, 6d, and what? 7p. So this gives the order, which is what? 1s. After 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 4f, 5d, and what? 6p. So it goes what? It goes in that what? In that order. So using the electronic configuration, you can write, you know, using the electronic configuration, using SPDF orbital notation, you can write the electronic configuration of an element, you follow the Aufbau principle. From there, you can determine the group, the period, and the block to which an element belongs. Let's say we take sodium for example. Sodium is 11. So if I were to write the electronic configuration, it will be equal to what? 1s2, then 2s2, then 2p6, then what? 2p6, then 3s1, 3s1. So that means sodium belongs to what? Group 1. Group 1. Period what? Period 3. The group is the number of electrons in the outermost shell. So sodium has 1 electron in the outermost shell, so it belongs to group 1. Then the period is the number of shells. So period 3. So period 1, 2, 2, 3. So period 3, which is the first shell, the second shell, and the third shell. Then the block is an S block element. The block is what? S block. So in the periodic table, sodium belongs to group 1, period 3 is also what? An S block element. Let's take another example. Let's take chlorine for example. Chlorine is 17. If I were to write the electronic configuration to be 1s2, 2s2, then 2p6, 3s2, 3s2, then 3p or 3p5. So you have to follow the order. You follow the Aufbau principle. You feed 1s before 2s. So for the electronic configuration, we can tell that was chlorine belong to what group? What? Group 7. The group is the number of electrons in the what? Outermost shell. So the third shell is the outermost shell. So it has what? 2 plus 5, which is equal to what? 7. So 2 electrons on the S subshell and 5 electrons on the P subshell. So 2 plus 5 is equal to 7. So it belongs to group 7. Then the block is what? A P block what? P block element. So if you look at the periodic table, chlorine belongs to group 7, period what? Group 7, period 3, and it's what? It's a P block what? Element. The period is period 3. Yes, group 7, period what? Period 3. The period is 3. And it's also what? EP block what? EP block element. So it's as simple as what? ABC. You have to follow the principle. You have to follow the order. You start filling from 1s to 2s to 2p to 3s. You must follow the order so you can get what? The accurate result. So representing electronic configuration. So this is how you represent the electronic configuration. This is the number of electrons, which is the number of electrons. That is the number of electrons. This is the subshell, and this is the principal quantum number, otherwise known as what? The number of what? The number of shell. So it's as simple as what? A, B, C. So you have the 1s2, 2s2, you know, just you follow the normal pattern in building what? The electrons. So this is the number of electrons, This is the principal quantum number, which is the number of shell, and this is what? The sub shell. So these are questions for us to attempt. This is a typical example of an exam style question. So we want to use 1s2 notation to give the electronic configuration of the atoms with the following what? Atomic what? Numbers. So based on our work on Aufbau principle, the building principle, then following the what? Order. So we have to write the electronic configuration of an element with atomic number 16. So electronic configuration is what? 1s2, then 2s2, then 2p6, then 3s2, then you have 3p or 3p4. So from this we can tell the group to which the element belongs. So this element belongs to group 6 because the group is the number of electrons in the what? Outermost shell, and the third shell is the outermost shell. So this S subject have 2 electrons, P subject have 4, so 2 plus 4 is 6. Then the period is the number of shells. So it is period what? Period 3, and it's what? The block is what? It's a P block element. The block is what? P block. Now let's take another one, 9. So it will be 1s2, 2s2, then what? 2p what? 2p5. So you can see that this element, it belongs to what? Group what? Group 5. Sorry, group 7. It belongs to group 7, which is 2 plus 5 is what? Was 7. The number of electrons in the outermost shell. So it belongs to group 7, and then period 2. Period 2. Yeah, period 2. And the block is what? It's a P block element. P. The block is P block element. So with that, you can just write the electronic configuration. You can tell the group. You can tell the period. That is it. It's as simple as what? A, B, C. So you can attempt C. You can write C on your own. Make an attempt with that. Write C. Write the electronic configuration for an atom with atomic number 20. State the group and state the word period, and try as much as possible to solve as many questions as possible. So I'm leaving this task for you. I'm leaving this task for you to solve. So this is a typical examination question based on what we've done. So please attempt these questions. They are very, very simple. Just listen to the lecture attentively and attempt the questions. And please feel free to reach out to me if you encounter any difficulty. So they are typical examination questions. They are exam style questions. The first one is an element has the electronic configuration. So the electronic configuration is there. You are now asked which block in the periodic table does this element belong to? Which group does it belong to? Identify this element. Then the B, which block in the periodic table does the element with the electronic configuration belong to? So please make an attempt and solve as many questions as possible. So I'm Mr. Joseph, your chemistry teacher. Please feel free to reach out to me if you encounter any difficulty. And please subscribe to my YouTube channel, like, comment, share, and feel free to reach out to me if you encounter any difficulty. I'm always there for you. I'm Mr. Joseph, your chemistry teacher. Thank you for listening. Mr. Joe, your chemistry teacher. Thank you for listening.